Chapter 13 has to do with equilibrium. We touched on it just briefly in the last chapter, and now we're going to talk about it some more. So what is equilibrium? As the name implies, it has to do with the forward reaction and the reverse reaction. So a lot of times when a reaction starts, products are formed, but then depending on the reaction, sometimes some of the products can react with each other to form the reactants, and so they can go back and forth. So a lot of times a reaction will sort of stop, or appear to stop anyway, at a mixture of products and reactants. And this is called a dynamic equilibrium. And the word dynamic is there because it seems to have stopped, but in fact it's still moving. So a dynamic equilibrium is when you have a forward reaction giving us products and a reverse reaction happening at the same time, where products give the original reactants back. So you've got a forward reaction and a reverse reaction happening together. And equilibrium is reached when the rate of the forward reaction equals the rate of the reverse reaction. So that's why I said it appears to have stopped, because the concentrations don't change. They stay consistent. However, it doesn't mean that the whole reaction is stopped. We still might have some forward reaction, but at the same time we have the reverse reaction, and because they're equal to each other, the concentrations don't change. So I like to use this example of an elevator. Say you're, especially if you can watch from afar. So if you've got one of those elevators with the glass windows in it, and you see that there's 3 people that get on the first floor, and so you can see 3 people in the elevator, and then it gets to the second floor, and 2 people get off and 2 people get on, and maybe you can't see it from afar, but because when it gets to the floor, it's kind of closed off. So you see 2 people get on, 2 people get off. It goes up to the 3rd floor, and maybe one person gets off, but another person gets on. So from afar, it looks like there's always 3 people. There is always 3 people on the elevator. It's not the same 3 people. So as long as the rate of people getting on and off is the same, then in other words, the forward and reverse reaction, then overall the concentrations, or the number of people in this case, or the concentrations of the reactants and products, stay consistent. And so it looks like nothing's happening, but in fact it's dynamic because they're still reacting, just that they're equal, so they cancel each other out. So another example might be like this U-shaped tube. There's constant mixing back and forth through the lower portion of the tube, but notice that it stays constant. The levels stay constant, even though maybe the water keeps mixing, or the 2 sides of the tube keep mixing, as long as they're at the same rate. Then the system appears static or stationary when in fact it's in constant motion. Okay, here is an example of a reaction. This is, we'll just let me get my pen going. Okay, so carbon monoxide and hydrogen. This is called the methanation reaction. If you take carbon monoxide and hydrogen, you can get methane and water. Anyway, what I want you to notice is that this is over time, this reaction right here, and these are concentrations, so moles of substance over time. So notice that, and in this case, they happen to start with 3 moles of hydrogen and 1 mole of CO, and of course 0 of the 2 products. And so the H2, the concentration starts to decrease over time because it's getting used up. The same thing happens, the carbon monoxide starts to decrease because it's getting used up. One thing you might notice is that the moles of H2 are going down faster than the moles of CO because it's a 3-to-1 ratio. But also look at the products. At the beginning, they're at 0 because there's no products, but as the reaction continues, the products start to build up, and they happen to be the same because they're 1-to-1. Isn't always the case. But anyway, the moles of the products start to rise. Notice that we get to a point then where the moles of H2 levels off, the moles of CO levels off, and the moles of the products level off. When they start to level off and they don't change anymore, that's when we're in equilibrium. And so these are the equilibrium amounts. And of course, this is specific to this specific reaction. They may look different. And as we'll see in a minute, it doesn't matter if we start with 3 moles and 1 mole. You can start with anything. This reaction will always come to an equilibrium where the levels will balance out. This graph over here is showing the rate of the reaction versus time. So notice that the forward reaction starts out very fast. It's reacting. Over time, the forward rate starts to slow down, as most reactions do, because the reactants are decreasing, and so the reaction rate slows down. At the same time, at the beginning, the reverse rate is not happening. I can draw a little arrow going back that way. The reverse reaction starts out at 0 because there's no products to even react with each other. But as they are formed, the reverse reaction picks up. And so the reverse reaction picks up, the forward reaction slows down. There comes a point where the two are equal to each other, and it levels off at that. So this is when you're in equilibrium, when the forward rate equals the reverse rate. So this slide, I'm not going to read it all, but it's kind of what I just said on the last slide. The reverse reaction rate will start at 0, but eventually it picks up because products start to be around. So once the forward rate here and the reverse rate are equal to each other, then we're at equilibrium. So I also said this earlier. Note that the H2 is used up 3 times as fast as the CO. That's because they are a 3-to-1 ratio, and they also end up with different equilibrium concentrations, and so the amounts don't have to be the same. Final equilibrium concentrations will depend on what you started with, what the reaction is, what the stoichiometry is, and like I said, we'll talk about this in a minute, it doesn't have to be, you don't have to use 3 times as much initial concentration of H2 over CO, but that it will get used up 3 times as fast will always be true. So no matter the starting concentrations, the ratio, it turns out the ratio of the final equilibrium concentrations will always be constant. So that's where we're going. So, all right, in another example, nitrogen and hydrogen are reacted to give ammonia. This reaction also does not go to completion. So a lot of times what we do is represent the equilibrium status with this double arrow. So an equilibrium is established where all 3 species are present, products and reactants. Not all the reactants get used up. It kind of reaches this, what they call a set point, where it just doesn't want to go any further. So let's again look at an example. Suppose we place 1 mole of nitrogen and 3 moles of hydrogen in a reaction vessel, and we let it go. It'll get to equilibrium. What will the composition of the equilibrium mixture be if it contains 0.080 moles of NH3? So at equilibrium, what will the other concentrations be of the nitrogen and the hydrogen at equilibrium? So to do that, we're going to set up a little chart. I like to call this the ICE chart because it stands for initial change equilibrium, and so an ICE chart. And so what we're going to do is kind of follow the concentrations throughout the reaction. So the question told me that I have 1 mole of nitrogen and I have 3 moles of hydrogen. And at the very beginning, before the reaction takes place, I don't have any ammonia because the reaction hasn't taken place. So I put a 0 in there. Then change. How will this reaction change over time? Well, we don't know exactly how much is going to be lost, but we do know, because so they're each, the nitrogen may lose a certain amount, the hydrogen may lose a certain amount, the amount of NH3 is going to increase, and we don't know the exact amounts, but we do know the relationship to each other. So I'm going to call X the decrease in nitrogen. So throughout, until it reaches equilibrium, some of the nitrogen is going to react, and I'm going to call that amount X. I put minus X because it's decreasing. The hydrogen, because it's a 3-to-1 ratio, I'm going to lose 3X of the hydrogen. And again, because of stoichiometry, I'm going to gain 2X of NH3. So for every 1 nitrogen that reacts, 3 hydrogen will react, and we will produce 2 ammonia. So that's where these come from. And then at equilibrium, we can see how much we have. We have whatever we started with minus whatever we lost. Here, whatever we started with minus whatever we lost. I think I'll use a different color here. And then here, what we started with 0. In this case, because the products are being formed, that's why it's a plus. And so at equilibrium, we have 2X. Okay, so now we have to go back to the problem, and it tells us that there is 0.080 moles of NH3 present at equilibrium. So what that means is now we have a way to find out what X is. That means that 2X equals 0.080, because that's how much was formed, 0.080, that's 2X. So that means X equals 0.040 moles. So now we can plug that in to the other parts of this equation, and we can figure out how much nitrogen and hydrogen there is. So if we plug in 0.040 into X here, then we have 0.96 moles of nitrogen left. We have 3 minus 3X, so 3 minus 0.120 equals 2.88 moles of the hydrogen left, and then we already knew that we had 0.080 moles of the ammonia present. And so hopefully you'll understand. If you didn't, you might want to go back and listen to me going through this, because we are going to be using these ice charts not just in this chapter, but we're also going to use it in the next 2 chapters. And so it's a really useful tool to help us solve our problems. I think it would be impossible if we didn't have the stoichiometry relationship between the component, with the 2X's, so that we can only have 1 unknown rather than 3 unknowns. All right, so we can create something called the reaction quotient. For the general reaction, A plus B gives me C plus D in equilibrium, we can create the reaction quotient, and it looks like this. The reaction quotient is a mathematical expression where we look at the amount of products divided by the reactants, and they are all raised to their coefficient. This is related to the fact that it is a 1-step ratio, so it kind of has to do with rate laws, and I think we talk about that later. But the reaction quotient is take the products in brackets, which means, remember, molar concentration. So molar concentration raised to the coefficient of the products divided by the reactants. And if there's more than 2, then you just keep multiplying them. If there's only 1, then you just have 1. We can calculate this QC at any point in a reaction, and so the numeric value for Q will vary. Sometimes we calculate it at the start of a reaction and we want to find out what's going to happen. But the key is that if we're at equilibrium, the value of Q will become what's called Kc, or the equilibrium constant. So at equilibrium, Qc becomes Kc. And so the same reaction, the same quotient, we have the same quotient, but if it's equal to Kc, we know that we're at equilibrium. So the equilibrium constant expression is always, again, products over reactants raised to their coefficients. And it's important to note, so K will have the same form as the reaction quotient Q, but K means it's at equilibrium. Q could be at any point in the reaction. And so we can actually find out, if we know what K is, we can find out what Q is, and we'll know if we're at equilibrium or not. And we'll actually talk about that in just a minute down the line. So, like I was saying, that we saw in that equilibrium, every reversible system has its own position of equilibrium under a given set of conditions. What I mean by that is if it's gas, particular pressure and particular temperature. So it may change if you change temperature and pressure, but if you don't do that, then everything sort of gets to the same set point. And so that value of the equilibrium constant, the Kc, will be the same as long as that constant, as long as the reaction is at equilibrium. Kc will be the constant no matter what we start with. It doesn't matter if we start like we did earlier with 1 mole of CO and 3 moles of H2, or any amount of reactions, or even if we start with products, we come to the same set point or the same equilibrium constant. And so it is dependent on temperature of the system, and it is dependent sometimes on pressure. But if that remains constant, then that's the set point. This reaction will always come back to that ratio. Kc or Qc, neither of them have units. Okay, so the value of Kc then can help you determine the extent of a reaction. If K is very large, that means that your numerator is greater than, so when we say very large, obviously anything over 1 indicates that products are more prevalent. So if it's equal to 1, that's when then products and reactants are equal, because we have products over reactants. If it's greater than 1, that means products predominate. But generally speaking, we kind of go with 1,000. Let's see what my slide says. Yeah, so usually if we say it's over 1,000, if Kc is over 1,000, then we've got like 99% products. If Kc is very small, meaning very much smaller than 0.001, then we have 99% reactants. A very large Kc would mean that the products are nearly all products. A very small Kc would mean that mostly reactants are present. Now, just keep in mind that the value of K gives us no indication as to the kinetics or how fast the reaction goes. It only tells us the set point in terms of concentration. Okay, and then, like I said earlier, we can determine if a system is at equilibrium or not, and we can decide what direction it will go to get to equilibrium, and we do that by comparing Q to K. So if Q, let's remember we've got K is products over reactants. So if Q is greater than K, that means that there's too many products. And so to make Q get smaller, we're going to have to shift to the left to to make more product, or more reactants. Sorry, shift to the left to make more reactants, because we need to get rid of products, make more reactants to make this ratio come down. If QC is less than KC, then in that case, that's the opposite. We'll do another color here. If Q is less than KC, that means that in order to get to K, Q has to get bigger. To get bigger, we have to increase the numerator. So that means we have to make more products, which means the reaction has to go right toward products. And of course, if Q equals K, then we already know we're at equilibrium. All right, so let's look back at this equilibrium that we looked at earlier. All right, we have a 50-liter vessel. We have 1 mole of nitrogen, 3 moles of hydrogen, and 0.5 moles of NH3. Is the system in equilibrium? And if not, which direction will it go to get to equilibrium? They say at 400 degrees, and then they tell you the K for the reaction at 400 degrees is 0.500, and so we don't have to worry about the temperature, just that the Kc is at the temperature we're looking for. So what we can do is we can plug in to the Q expression and find out what Q is, and then we'll compare it to K. All right, so do keep in mind that all these values, I know the very first problem we looked at was moles, but for the most part, we're looking at concentrations, molar concentrations. So notice in that problem, it said 1 mole of nitrogen, 3 moles of hydrogen, and 0.5 moles of NH3, but it also said it was in a 50-liter vessel. So we need to find the concentration, we need to divide by 50. And we do have to do this before we do anything else, because they won't necessarily cancel. All right, so that means we have 0.0200 molar N2, 0.0600 molar H2, and 0.0100 molar NH3. So now we're going to plug that into our expression. There's our Q expression. Don't forget, it's so easy to overlook these exponents. So don't forget the exponents. So we're going to plug in 0.0100 squared divided by 0.0200 divided by 0.0600 cubed, and that equals 23. So at this set of conditions, the Q is 23. Well, we know that that K is 0.5. So obviously Q is greater than 0.5, so it's not at equilibrium. And because Q is greater than K, the reaction has to go toward the left. To try to make Q smaller, we need to make more reactants, so it's going to go to the left as it approaches equilibrium.